Okay, everyone, welcome back. I was just checking to make sure that all of the internet issues are fixed and I have a steady stream. So even though this is technically being streamed during off hours, I just wanted to check that everything was fine. So this will hopefully be uploaded pretty quickly. Anyway, so picking up where we left off from yesterday, we had just discussed this notion of, well, thinking of modulus for complex number z. Now, whether we're thinking about that z written in this x plus iy notation or whether we're thinking about that as an ordered pair xy, we very well aware of the notion of distance or length of this vector. So if we're thinking about this as a vector with terminal point indicated by this ordered pair, then that distance we saw was this quantity that we called the modulus, right? So the modulus of this complex number is square root of x squared plus y squared, right? Or thought of another way, of course, this is square root of the real part of z squared plus the imaginary part of z squared. Right? This is a more convoluted way of writing it, but that's exactly what is being conveyed here. Of course, an alternative way of thinking about this is that if you square the modulus, well, that's the sum of the squares of the real and imaginary part of the number. So however way you want to think about this, we of course first encounter this as the distance from the origin to the point xy. Okay, so that's the length of that vector, and that's what the modulus is computing here. So I mentioned that one of the potential uses here for this is that it gives us it doesn't quite give us the ordering that we have for real numbers, but it gives us something that's kind of sort of close to it for complex numbers, but but of course not on the complex numbers themselves, but rather on their modulus or on their moduli, on those lengths, these distances here. And so to see that, for instance, textbook uses a simple example here. Actually, I'm just going to pick some random numbers here. So let's let z1 be the complex number, let's say like minus 4 plus 2i, and let z sub 2 be the complex number, we'll say 1 plus I. Okay. And so if we compute the modulus of z sub 1, what do I get here? This is square root of minus 4 squared plus 2 squared. So this is, so minus 4 squared, that's 16, plus 2 squared is 4, so this is square root of 20. Okay, and my modulus of z sub 2 is square root of 1 squared plus 1 squared, so it's square root of 2. Okay, and so the modulus of z sub 1 is larger than the modulus of z sub 2, right? So I can say that. So while I can't say, it doesn't really make any sense to say the complex number z sub 1 is larger than the complex number z sub 2. We know that that doesn't really make sense for ordered pairs. But I can say this, right? And so what does this mean? Well, it means that z sub 2 is closer to the origin, right? So this is closer to the origin, right, than z sub 1, right? Okay. And so while it's not exactly an ordering in the sense that we're used to, it does give us some kind of way of quantifying some notion of order here. Okay. All right, so sticking to this point, let's remind ourselves from previous algebra experience here. Again, I'm going to abuse the fact that you guys have already seen a ton of, you've already done a ton of stuff in the plane, right? So dealing with quantities in the Cartesian plane is something that you've been doing for many, many years at this point. So for instance, suppose I have 2 points, right? So say x sub 1, y sub 1, and another point we'll say x sub 2, y sub 2. Okay. Then let me find, where did I put my, I want to draw some nice lines for you all so that my pictures aren't too horrible. Don't worry, we'll get to the horrible pictures eventually. Let's connect these and ask, well, what's the distance, or what's the length of that line segment, rather? Right? You all could easily come up with the distance between these 2 points. So this distance, right, the length of that line segment between those 2 points, we already know what that is. That is the square root of the difference in the x slots plus squared plus the difference in the y slots squared. All right, so you could have told me that a long time ago. Of course, where does this come from? This is literally just the Pythagorean theorem, right? So this comes from the Pythagorean theorem and drawing in a triangle here. Okay, so no arguments there. All right. Well, how can I relate this to what we've been doing with complex? Maybe I'll pick a different color here. Well, I could associate these to complex numbers, say z1 and z2. So we'll say that this is z2, and we'll say that this is z1. And if I associate to those complex numbers vectors, so we'll have this vector, say, emanating from the origin, going to that ordered pair indicated by x1, y1, and draw in another vector associated to z sub 2 here. Okay, well then in terms of vectors, what can I say about the vector that's directed, say, from z sub 2 to z sub 1? Right, what can I say about that vector? Well, without too much thinking, I can say that vector is actually the vector z sub 1 minus z sub 2. And thus the length of z sub 1 minus z sub 2. If you need to remember how this goes, because there's always a question about what direction a vector like this points in, it's terminal minus initial is how you remember what direction the pointing happens. So since z sub 1 comes first, it's the terminal point of this vector between 2 points. Okay, and so this length that I've written here should be the same as this. And in fact, that is exactly what it is, right? If you were to actually write this out, this is exactly what you get. Notice that it doesn't actually matter what order these appear in, right? Which absolutely makes perfect sense. In fact, we would be worried if that wasn't the case, right? And so the modulus of the difference of these complex numbers is, or can be interpreted as the length of that vector, okay, drawn in this picture. Okay, so note z sub 2, the modulus of z sub 2 minus z sub 1 is the same as the modulus of z sub 1 minus z sub 2. Okay, so no question there. And in fact, right, what we have just said here is that this modulus of z sub 1 minus z sub 2 is the distance from, say, z sub 1 to z sub 2. Of course, if you believe that it is a distance in a proper sense, it shouldn't matter whether we're talking about distance from z sub 1 to z sub 2 or z sub 2 to z sub 1, right? That should be symmetric. Okay, this is one of our requirements of anything we want to call a proper distance function, or if you've had experience with them before, a metric space. So this is the notion of a metric. Okay. All right, so this gives us a way of computing distances between complex numbers. Okay, so while we're taking care of some of these basic quantities involved in specifying distance, now that we have the modulus to be able to talk about distances between complex points, or between complex numbers, that is, points in the plane, this allows us to define some quantities in terms of this distance. right? So for instance, consider the set of all complex numbers z that are a specified distance r from a fixed complex number z naught. So the set of all complex numbers z that are a specified distance r from a fixed complex number z naught. So question, what is such a set? And so the answer, of course, since complex numbers are points in the plane, this is the same question as asking what is the set of all points in the plane that are some fixed distance r from some other point in the plane. It's a circle, right? This is the definition of a circle, right? This is a circle with radius r and center z naught. Okay, so this is a circle with radius r and center z naught. Of course, how do I actually denote this circle? Now we have a means of specifying the distance between two complex points in terms of the modulus here. And so I have a complex number z. That complex number is some distance, some specified distance from a fixed number z naught, and that specified distance is r. This is the equation for a circle with center z naught and radius r. So this is the equation for the circle with center z naught and radius r. Okay. This is very useful. Okay, we are going to use this characterization of a circle over and over again in this course. This is going to become completely second nature to you to think in terms of this notation. Okay. What if I change this just slightly? So what about, say, this? What region in the complex plane does this denote? Well, let's think about it for a second. All right, so here is z naught. Well, I said I wasn't going to draw bad pictures, but I really don't feel like, honestly, this thing is kind of wobbly, so I don't think I'm even going to give it a try. I'm just going to try to freehand it here. So there is my circle of radius r. You'll note that I left it dashed. Oh, that doesn't show up that well on camera. Well, it shows up okay, I guess, but let me go around it again. Maybe being a little more aggressive this time. There we go. All right, so I have this circle here. I have left it dashed or dotted here to show that I'm not actually including it. If I was including the set of all complex numbers that were on that circle, then I would make it dark. This is, if we're thinking of the set of all complex numbers z that satisfy this relation, it would be the interior of this circular region, right? So it wouldn't include the circle itself, it would just be the interior, right? If I made this not a strict inequality, then it would include the boundary as well. Now, I'm getting a little bit ahead of myself. This is something that we'll talk in detail about a little bit later. But this is just to give you like an immediate application of using this notation to discuss some regions that are going to be very, very important for what we do coming up, okay, in the next big block of material. Because ultimately in this class, our goal is to perform analysis of functions of a complex variable. Right, so we want to carry out calculus like you maybe have, are used to by now for functions of real variables or maybe even multiple real variables. We want to do that for functions of a complex variable. So that's our goal. And describing regions like this are going to be very important for us. Okay, so a couple other things, just kind of doing some bookkeeping here. So as I wrote before, you can think of the modulus, since we know the modulus of a complex number using the normal notation is this, we could think about this as the square root of the real part of z squared plus the imaginary part of z squared. Okay, that's an alternative way of thinking about this. Alternatively, we could think that if I square the modulus, this is just the sum of the squares of the real and imaginary parts. So this is the real part of z squared plus the imaginary part of z squared. Okay, but what does this tell you, right? So thinking for a second, noting that the modulus is also always positive, well, this gives me the following fact. So the real part of a complex number, that is, of course, less than or equal to the absolute value of the real part of a complex number. Now, why did I say absolute value instead of modulus? Because the real part of a complex number is real. So this modulus is just the absolute value. Okay, and of course, because of this fact, this is less than or equal to the modulus of the complex number z. Okay, so let's think about this for a second. First of all, why can we not get rid of the equality sign here? Because the complex number z could lie on the real axis, right? It could actually just be a real number. And if it's a real number, and it's a positive real number, then the real part of it is some positive real number, and all these actually are equal. Okay, so these would all have to be equal in the event that z is real and positive. Okay, so that's why we can't get rid of the equality part of the inequalities. They can't make these strict in general. And the imaginary part of z is also less than or equal to the absolute value of the imaginary part, which itself is less than or equal to the modulus of z. So there's these basic facts. Now you might say, well, this is obvious, but it's nice to keep track of all of this stuff because you're going to be asked, you're going to be doing all kinds of different analyses involving complex numbers, and sometimes keeping track of certain conditions can be a little tricky, and it's nice to just keep this kind of running list of facts going in your head. Okay. All right. So, continuing on with some more facts, we have a very important thing. This is the last thing that tidies up our metric, if you know anything about metric spaces. This is one of our last requirements of a proper distance, proper notion of distance, I should say, is the triangle inequality. And the triangle inequality states that if I have two complex numbers, z1 and z2, and I consider the modulus of their sum, this is less than or equal to the moduluses summed separately. Okay. The name explains exactly where this comes from if you actually draw the picture. Right? I'm going to draw like the lower half of my parallelogram, right? So I'm going to draw, say, a z1. Okay, and then I'll draw a z2. Okay, so this is, we'll say z1. That is here. And a vector associated to z2 here. Okay, I'll do it like this. That's fine. So here's my vector associated to z2. Then this vector, which is the diagonal of that parallelogram I drew yesterday, is so this is an identical vector to z2. I knew I drew this a little bit longer, but just bear with me. Then this diagonal then is z1 plus z2. And so what's the triangle inequality saying? It's saying that the length of this triangular piece is less than or equal to the length of z1 and the length of z2. So looking at this picture, if this is a triangle, this seems obvious. When do you actually have equality? I'll let you think about that, right? So think, maybe a quick exercise. When do you have equality? Okay. So think about that. Okay. So you may have encountered the triangle inequality in different contexts, but here it is again, popping up here exactly where you're seeing this in the context of the complex plane. Okay. Now, using the triangle inequality, we can actually see, so this immediately implies a fact that is related, that the length of z1 plus z2 is greater than or equal to the absolute value of the modulus of z1 minus the modulus of z2. So the triangle inequality gets you here. How? Right. So here's the hint. Okay. I start with z1, and I do classic algebra trick. You've probably seen this in various contexts before. I add and subtract the same quantity. So I start with z1 here. I take z1, and to z1 I add z2. But if I'm going to have this equality sign here, I had better subtract z2 as well. Okay. Well, now I can use the triangle inequality for this. And you might complain. You might say, well, the triangle inequality has plus here, right? Well, let's rewrite this so that we don't have any complainers. So I have z sub 1 plus z sub 2 plus minus z sub 2. There we go, right? Complaints are quelled now, hopefully. Okay. All right. And so, now what do? I use the triangle inequality. So I use triangle inequality, and what I get is that this is less than or equal to the modulus of z sub 1 plus z sub 2 plus modulus of z sub 2. Aha. Well, now I can subtract the modulus of z sub 2 from both sides, and that gives me that the modulus of z sub 1 plus z sub 2 is greater than or equal to the modulus of z sub 1 minus modulus of z sub 2. That gives me part of this. That gives me 1/2 of this inequality. So it's similar for the other half. Okay, so it's similar for the other half, and that's where this comes from. Okay, now keeping track of all the various inequalities you're going to come across can be a little bit tricky. So thankfully there's a nice convenient thing that you can remember when it comes to both the triangle inequality and this companion inequality. And so here's the kind of main gist of what's going on. So in fact, I can, instead of just simply thinking about the sums of these things, I can actually include their differences as well. So z sub 1 plus or minus z sub 2, doesn't matter which, is less than or equal to the sum of the moduli separately, I should say. And similarly, the accompanying companion inequality, so if whether I'm adding or subtracting these complex numbers, the modulus is greater than or equal to the absolute value of the difference of the moduli. And so your textbook actually combines both of these facts. So maybe I'll label these 1 and 2. You can combine 1 and 2 together to get the following inequality, if you like, that the absolute value of the difference of the moduli of two complex numbers is less than or equal to z sub 1 plus or minus z sub 2. I'm taking the modulus of that, and that, by the triangle inequality, is less than or equal to the sum of the moduli separately. Okay, so here is kind of a nice thing that ties all of those together. Okay. One more thing, and then I'm going to do a quick example, and we'll talk a little bit more. This might seem like a weird approach because we're just kind of shotgunning all of this info about this basic stuff at you. You should kind of view this as just laying the groundwork for a lot of the computations and a lot of the derivations we're going to do later. And so, like, if I'm deriving some fact about functions, a lot of that just relies on some of this underlying basic algebra stuff, and so in most cases, if you're confused about a step there, typically it's something that's going on here, which is why it's important that we talk about this stuff first. Okay. So, like I said, one more thing before I want to do an example. There's actually the generalized triangle inequality. You can prove this via induction. So the base case is the triangle inequality itself, and then for the inductive step, you just apply the triangle inequality again. So it's actually pretty easy to show. So generalized triangle inequality says you can actually do this for a sum of any number of complex numbers. So you have a sum of n complex numbers. If you take the modulus, then that is less than or equal to the sum of all of those moduli taken separately. Okay. And so the proof is induction. As I said, base case n equals 2 is triangle inequality itself, so that's true. And then the inductive step itself just requires a single application of the triangle inequality. So you're good to go. Okay. Now let's do one quick example here. Okay, of how we can use this to say something reasonable. So suppose z, which is a complex number, lies on the unit circle. What is the unit circle in our new snazzy notation? Well, it is the set of complex numbers z such that the modulus of z is equal to 1. Okay. So suppose that z lies on the unit circle. Okay. Then note that if I take such a z and I say consider the modulus of z minus 2, I know from those inequalities that I just took away. For instance, here, let's go back. Whoop. Here we go. So I know, for instance, by the triangle inequality, that this is less than or equal to the modulus of z plus the modulus of 2, which is just 2. Right? But modulus of z is 1 for z lying on the unit circle, so this is 3. And similarly, using 2, the modulus of z minus 2 is greater than or equal to the absolute value of modulus of z minus 2, which is the absolute value of 1 minus 2, which is the absolute value of minus 1, which is 1. And so, for a complex number lying on unit circle, I know, for instance, that the modulus of z minus 2 is between 1 and 3. Okay. Now, you might see that this is like a pretty simple computation here, and maybe you even have some other intuitive way you might have thought about that problem prior to seeing those inequalities. But the idea here is that for a lot of the stuff that's coming up, we're going to make use of these facts quite a bit. We're going to make use of these kind of basic principles to help us with our analysis. Okay. All right. So, in keeping with that, what I next want to do is to give myself more machinery for making some of these computations easier or maybe more palatable. Okay. And to that end, I want to talk about the notion of complex conjugation or complex conjugates. What is this? What is this? I butchered that word. Complex conjugates. I didn't know if I was going to say conjugation or conjugates. I got confused there for a second. Okay, so what is the notion of a complex conjugate? Again, you have likely seen this in any course that required you to do any kind of analysis where you're solving quadratics and using those roots to do something. So for instance, if you're finding eigenvalues, eigenvectors, if you're doing that in differential equations, linear algebra, wherever, when you dealt with complex eigenvalues, right? One of the main facts that you used in that course was that those complex eigenvalues were coming in conjugate pairs, right? Like that's the polynomials that you were dealing with, right, were such that all of the complex roots came in these conjugate pairs because they had real coefficients. So anyway, that's something that's not going to be true for us because we're going to be dealing with slightly more general polynomials that are allowed to have, say, complex coefficients. But if you have a polynomial that has real coefficients, all of them have to come in conjugate pairs, and so that's the context usually where you first talk about complex conjugation. But in case you haven't seen that, what's a quick way of saying what a complex conjugate is? Well, if I have a complex number z, then z bar is defined to be, so I read that as z bar, this is the complex conjugate of z, it's just x minus iy. So this is the complex conjugate of z. Okay. So first of all, what is maybe like a motivating thing here? Well, geometrically, I always like talking about geometric descriptions here. So if here's my x and y axes, and here's my z represented by x plus iy, where is z bar? Well, z bar is simply a flip, right? It is a reflection across the x-axis. Okay, so I took a complex number with real part x and imaginary part y, and I transformed it into a complex number with the same real part, but I replaced the imaginary part with minus that thing. So this is a reflection across the x-axis, and so z bar is here. Right, so here's z bar, and that's x minus iy. Okay. Okay. And so maybe even draw the picture to indicate that it's a reflection thing that's happening here. Okay, but what is the point of such a thing? So you might have already been thinking about some of these things. You might have already been thinking about maybe some of the algebraic properties. There's some easy things to say here. So one, note that if I take a complex number, I conjugate it, and then I consider the conjugate of the conjugate. I have a funny joke to tell you about this, so I'll do that when I'm recording live sometime. I will tell you all a funny joke about this notation. I might wait until the next big block of material we're in, because there's where it's really going to shine, but this notation can get a little bit funky when you're conjugating multiple things, or when you just have bad You have notation with a lot of lines, a lot of horizontal lines. It can be bad. So anyway, what if I take the conjugate of the conjugate? Well, that's just the... No, why did I do that? That's not what it is at all. Right? It is just the complex number z itself. Okay. Also, the modulus of the conjugate is the same as the modulus of the complex number z itself. So here's two quick facts about conjugation. So if you don't believe this one, just think for a second, right? So I'm taking the modulus of z. This would be square root of x squared plus y squared. I'm taking the modulus of z bar. This would be square root of x squared plus minus y squared. Oh, okay. So the minus sign doesn't matter at all there, right? So, okay. What are some other quick facts? So let's say that we have a complex number z sub 1 given to me by ordered pair x1, y sub 1. And I have z sub 2 given to me by ordered pair x sub 2, y sub 2. Okay, what if I consider, say, the conjugate of the sum z sub 1 plus z sub 2? Well, okay, so I know how to sum these together pretty easily. So this would be writing now in my x plus iy notation. This would be the conjugate of x1 plus x sub 2 plus I times y1 plus y sub 2. Okay. Conjugating a number that looks like this just means replacing that plus with a minus, right? So this is x sub 1 plus x sub 2 minus I times y sub 1 plus y sub 2. Splitting these up, of course, I'm going to get x sub 1 minus I y sub 1 plus x sub 2 minus I y sub 2. I'm just distributing that minus I there. But what is this? It's the conjugate of z sub 1 plus the conjugate of z sub 2. So conjugation splits up across sums. Okay, so maybe that's a third fact to add here. And if I have a sum of two complex numbers, I conjugate that sum. Well, this is just the sum of the conjugates, right? This is our favorite type of statement to make in all of math, right? So our favorite type of statement to make in math is the blah of the bleh is the bleh of the blah. That doesn't sound too enlightening, but here in this case it is the conjugate of the sum is the sum of the conjugates, right? The product, or the limit of the product, is the product of the limits, right? This is our favorite kind of math statement to make, and so we're happy because we get to make it here. Okay. Well, I have some more stuff to add. All right, so a next fact that is also true here is, and for similar reasons, if I consider the conjugate of a product, what do you know? It's the product of the conjugates. Right? Okay. If I consider the conjugate of a quotient, here we're touching also on that bad notation joke that I'm going to tell. Okay, because we got too many horizontal bars showing up here, right, in our notation. That's scary to us. Okay, well, this is actually the quotient of the conjugates. Oh, we are really getting scared, right? A lot of horizontal lines being thrown around here. Okay. All right, and so these are true, and of course I can't have the denominator be 0 here. That makes perfect sense. Even you might notice, right, that the conjugate of 0 is still 0. You might also notice that if z is real, right, i.e. that's true, when the imaginary part of z is equal to 0, then we'll call this a sixth fact, right? Then the conjugate of z is equal to z. In fact, this doesn't just go in this direction, this goes in the opposite direction, right? So a complex number is equal to its own conjugate if and only if it's real. So this is actually an if and only if statement. So actually, z is real if and only if z bar is equal to z. Okay, so if you take a real number, right, that thinking of it sitting in the complex plane on the real axis, you conjugate it, well, nothing happens, right? Going back to our description of this as a reflection, of course, the points on the x-axis are fixed points under that transformation, right? They don't get moved at all by reflecting along or across the x-axis. Okay. All right. So now let's think for a second, what do I get when I take a complex number z and I add it to its own conjugate? Let's do that real quick. So this is x plus iy plus x minus iy. Okay, well that's the iy and minus iy cancel. And what I get is 2x, which of course is 2 times the real part of z. And so I get my next fact, which is that the real part of z is z plus z bar divided by 2. Okay. Similarly, if I look at z minus z bar, I get the following fact, that the imaginary part of z is z minus z bar over 2. So if you want to prove that in a way very similar to how we showed number 7 here, you do the exact same thing. Instead of doing z plus z bar, you do z minus z bar. And that gives you the same thing. Oh, sorry. What am I doing here? Yeah, 2i. Okay, maybe I should do this, right, so that I don't just leave this up to you here. So let's do that real quick. So what is z minus z bar? All right, so z minus z bar then is x plus iy, right, minus x minus iy. So the x's cancel, and I'm left with 2iy. So that is 2 I times the imaginary part of z. Okay. So I got to divide by 2i here. Okay. Now it has a hope of being right? It had zero hope of being right without that 2i there. Okay. Well, we took complex number z and added it to its conjugate. We took complex number z and subtracted its conjugate from it. We got special relations here. So what else? What else can we do? Well, naturally, the question you might have is, what happens when I take a complex number z and I multiply it by its conjugate? Okay. Well, let's just do this, right? No reason to leave it up to the imagination. I would have x plus iy times x minus iy. What do I get when I do that? Well, let's FOIL this out here. Because of the plus and minus, of course, I have a difference of squares things going on here, right? The mixed terms cancel. And so what I get is x squared, right, minus xiy plus xiy. So those cancel. And then what I have left here is minus I squared y squared. But of course, I squared is minus 1, so this is x squared plus y squared. What is x squared plus y squared? Well, that's just the modulus of z squared. And it's starting to come together. And so, we have the following fact. What was my last fact? Number 8. So here's fact 9 in this running fact list. Z bar is equal to the modulus of z squared. So this is a nice fact. You might not see right off the bat why this is nice, but I'm going to go ahead and spill the beans and tell you that this tells you exactly how to have a pretty nice, easy, closed form way of writing the inverse, the multiplicative inverse of a complex number. And so, let's start with z bar divided by mod z squared. Remember, mod z squared is just, so the modulus of z squared is just a real number, right? So dividing by it's no problem at all. This is equal to 1. I'm not even rewriting anything. All I'm doing is just making sure you see what it is that's going on here. So I took a complex number z, multiplied it by a thing in parentheses here, and I got 1. What does that tell me? It tells me, since the multiplicative inverse is unique, that has to be it. So the multiplicative inverse of a complex number z can be thought of as the conjugate of z divided by the modulus of z squared. You could find this through trial and error, just looking up, right, like what would work algebraically to make that work out. That's exactly what we did when we actually wrote out the formula. In fact, we could have not done this at all. We could have actually just used the formula we already had and noted, hey, like this is just a clever way of rewriting. Right, now that we know what the conjugate is, we have this formula, but this is another way of thinking about it. So this, of course, tells you exactly where we get that method that we got for dividing complex numbers, right? So again, just to do another example of complex numbers division. So if I have, say, minus 1 plus 3i divided by 2 minus I, to actually do that division, the kind of simplest thing to do is to multiply top and bottom by the conjugate of 2 minus I. So I would have minus 1 plus 3i times 2 plus I over 2 minus I times 2 plus I. So that in the bottom we're going to get the modulus of 2 minus I squared. And so what do we get here? So multiplying this out, I would have minus 2. So we have minus 2. Here I would have minus 3. So that would be minus 5. And then the mixed terms would be minus 1i plus 6i, so plus 5i. Okay, and that is over the modulus of 2 minus I squared. So that's, what, 5? But so to see that, of course, the mixed terms cancel out. I would have 2 squared minus I squared. So that's 2 squared minus minus 1. So that's 5 here. And so actually, that's top is easily divisible by this. So this is minus 1 plus I is that quotient. Okay, this is the trick that we did yesterday, right? Okay. All right. And so this also allows us to keep tossing in facts to our list. So maybe talk about fact 10 involving moduli, right? So if I take the modulus of a product of complex numbers, this is the product of the moduli. Okay. Where does this come from? We can actually get it directly from here. Right, we could actually get it directly from this previous fact. Okay. What else is true? Well, I can apply the same reasoning here for quotients. Modulus of quotient of z1 and z2 is the quotient of the moduli. Okay. All right. Okay. So if I had to prove which one to do, let's do this one. So let's see how we would use this previous fact to do this. So I claim that I can use this fact to get it done. The idea is if I look at the moduli of this product squared, okay, this is by this previous fact. I've already taken it away again. I can rewrite this as z times z bar. So I can rewrite this as z1, z2 times z1, z2 bar. And now I know that I can split this up as z1, z2 times z1 bar times z2 bar, right? I can split the conjugation up because of one of these first facts. I think this was fact what? This was fact 4 in our in our fact list. Right, there it is. Okay. Okay. And now I can rearrange these. So I can rearrange these as z1, z1 bar and z2, z2 bar. If you like. But of course, then this is by the same formula that we started out with from number 9. This is mod z1 squared times mod z2 squared. Right. So this is mod z1 times mod z2 squared. Up. Right, and then I can take the square root of both sides, so I'm good to go. I have exactly the formula that I wanted. Okay, just being careful with the bookkeeping here. Okay. All right, so one more example of an application of some of these facts as it pertains to some of the computations you're going to be doing. So for instance, note, so consider this an exercise, or an example rather. Note that from that previous property, if I have the modulus of z squared, that is actually equal to the modulus of z squared. Or if I have the modulus of z cubed, that is actually equal to the modulus of z all cubed, right? Sounds like I'm saying the exact same thing. It turns out it doesn't matter because we have this equality from that last fact. Okay. Thus, if z is a complex number inside the circle centered at the origin of radius 2, what does that mean? Z is a complex number inside the circle centered at the origin of radius 2. This is just a long-winded way of saying that the modulus of z is strictly less than 2. Okay, using our previous notation here. All right, then, say I wanted to obtain a bound on a polynomial expression, z cubed plus 3z squared minus 2z plus 1. So I wanted to obtain a bound on that modulus. Using the generalized triangle inequality, this is less than or equal to the modulus of z cubed plus, I can actually pull the 3 out since it is positive, the modulus of z squared plus 2 times the modulus of z plus 1. Using this previous fact here, this of course is equal to mod z cubed plus 3 times mod z squared plus 2 times the modulus of z plus 1. Since the modulus of z is strictly less than 2, this is strictly less than 2 cubed plus 3 times 2 squared plus 2 times 2 plus 1. So that's 8 plus 12, that's 20, plus 5, so that's 25. So using these algebraic facts, we know we've obtained a bound on the modulus of some polynomial expression. Okay. These sorts of things are going to be important going forward for the types of analysis that we want to do. Okay, so that's why it's important to know all of these algebraic properties. And you're going to get to know them through a lot of practice. Okay, and so what else? Well, the last thing I wanted to mention today is polar form or exponential form for a complex number. So polar form. So sometimes referred to as exponential form of a complex number. Okay, so what's the idea here? Well, I'm thinking of a complex number z as an ordered pair, or of course x plus iy. So again, here's my typical picture. There's my point z represented by ordered pair xy. Well, what I want to do is to remember polar coordinates for, so this is rectangular coordinates. This is sometimes called rectangular form. Okay, of a complex number. So the rectangular form is just its typical description in Cartesian coordinates, x, y. Okay. Well, you have been exposed to, at some point in your math career, the notion of polar coordinates. What's polar coordinates? Well, associated to this complex number z, this ordered pair xy, there is a length. Right? This length is typically written as little r here. Okay, and of course there is an angular measurement measured from the positive x-axis. Here's x-axis, here's the y-axis. Measured from the positive x-axis, I have this angular measurement theta. And so the parameters r and theta can be used to specify a point. The quick intuitive way of thinking about it is, how do I specify xy? I measure out an angle. So where I am in the plane, like how far around I am relative to the positive x-axis, is determined by theta. R tells me how far out I am, right? R equals 0 means I'm at the origin. If R is non-zero, then I'm somewhere out here, right? So R tells me how far away from the origin I am, and theta tells me where around the plane relative to the positive x-axis I am. Okay, so this is enough. R and theta are enough. Okay, and so what is the usual way that we do polar coordinates? Well, polar coordinates are defined by the following relations. X is determined as r cosine theta, and y is determined as r sine theta. So once you see this, and once you remember that cosine and sine are used, right, in the definition of a circle, right, then what you understand is, oh, polar coordinates are really just a way of taking any point in the plane and viewing it as a point on some circle of some radius. So that some radius here is little r, and then theta is just some angular value around the circle. So all polar coordinates are is just taking a point in the plane and saying that point is on some circle centered at the origin. Okay, that's got some radius and some angular amount theta around the circle. Okay, well, if we've done this replacement, then, well, I can just straight up say if x is r cosine theta and y is r sine theta, then we're good to go there. Okay. And we should also note that this r is not mysterious to us, right? This r is something that we actually have been talking about recently. That is just the distance from our complex number to the origin, or the modulus of z. And so I could just as well replace this with this modulus of z, just the same. So I'm not going to do that for a second. I'm going to leave it as little r here. Okay, and so switching back to this notation, then this is really me writing z as r cosine theta plus I times r sine theta, or factoring the r out, r times cosine theta plus I sine theta. Okay, where again this little r is just the modulus of z. Okay. Written in terms of x and y, of course, this is square root of x squared plus y squared. And you might say, oh yes, that is exactly the relationship I remember between x, y, and r back when I first learned polar coordinates, right? This was actually one of the ways you found r in that case. Okay. All right. Now, of course, right, there's something you're giving up here, right? You're giving up something by switching to polar form. So what's the reason for switching to polar coordinates, that you first encountered? Well, polar coordinates make certain things a lot easier to describe. Describing things like an Archimedean spiral, right, is a lot easier in polar coordinates. Describing circles, parts of circles, arcs of circular things is easier in polar coordinates. Those equations are very, very simple, whereas describing them in rectangular coordinates can get a little nasty. Okay, and so that's one of the first things that's nice about polar coordinates. But you are giving something away when you do polar coordinates, and the thing you're giving away is unique representation, right? So rectangular coordinates, right? When I say I have coordinates x, y, right, that are pinpointing some point in the plane, it's kind of it's unambiguous, right? 2 points are equal if and only if x and y are equal to each other. But with polar coordinates, it's a little tricky because theta, of course, is an angular value. And so if all you're thinking about is describing a point, right, how do you differentiate between, say, going theta amount and theta plus 2 pi amount, right? So instead of going directly to the point in question, you go around some number of times and then to the point, right? Well, you're specifying the same point in that way, right? And so there's some non-uniqueness involved in this angular value, which is always the sort of thing that comes up when you're dealing with trig equations, right? And of course, the reason for that is since r is determined in terms of x and y from this, how do you determine theta? You might recall that tan theta is y over x, right? And so finding theta angular values means nailing down a theta from that trig equation, which involves being careful there. Okay, so you have to make sure that you take that into account. Okay, and so what do I do to kind of keep track of that? So when I have a z written in polar form in this way, in order to have kind of a nice way of keeping track of this theta, okay, I want to discuss the argument of a complex number. So what is the notion of an argument of z? Okay, well, each theta value is an argument of z. And the set of all such values is called argz. the principal argument of z. So this is the principal argument of z, or I should say the principal argument of z, or the principal value of arg z. If I want to match what the textbook says, is denoted as capital A arg z. And to describe what that is, so capital A arg z is the unique value theta such that it is between minus pi and pi. Then arg z can be thought of as big A arg z plus some multiple of 2 pi. So n is some integer multiple of 2 pi. Now, this might seem like a pretty convoluted way of thinking about this, of getting rid of the ambiguity and dealing with the fact that there's infinitely many values for any given complex number, there's infinitely many values of theta that you could use to describe it in polar form. This nails down exactly what it is that's going on, though. And so this is what we're interested in, is finding this principal value, or this principal argument. That's what we're interested in. Okay. So just to also tidy this up, note when z is a negative real number, arg z has value pi, not minus pi. Okay. So you draw a picture, you see why we have to actually specify that here to keep track of any ambiguity that could creep in. Okay, so I'm going to do one example, and then I'll pick up here tomorrow. So let's do a quick example of argument here. Let's compute the argument of minus 1 minus I. What is this? Well, let's think for a second. Minus 1 minus I, where is that in my plane? Minus 1 minus I is like here. Right, here's minus 1 minus I. That's in the third quadrant. Okay. What is this angle? Well, minus 1 minus I is in the third quadrant. Of course, it's on the line y equals x. Right? And so what's the angular value it takes me to get from positive x-axis to this line y equals x in the third quadrant? Well, so here's pi over 4, pi over 2. Here's pi. What is this? It's in third quadrant. It is, so I would have to go over pi here, right, in order to get there in this direction. So why don't I use the principal value that allows me to be between minus pi and pi here. So instead of going 5 pi over 4 here, I can go minus 3 pi over 4. And I'm good to go. So the argument of minus 1 minus I is minus 3 pi over 4. Okay. Now it might seem like kind of a lot of work to answer what should be a quick thing, but you get used to it here, right? You get used to quickly computing these things. And of course, if I wanted to talk about argz, that is the entire set of all possible theta values that would describe that point, that would be minus 3 pi over 4, right? Just following this, plus multiples, integer multiples of 2 pi, okay, for n in the integers. So z is the integers. Okay. All right. So, one more thing I wanted to note, and then I will be done for today. And that is, so if I have a complex number z in polar form, we saw that this was writing it as r times cosine theta plus I sine theta. Okay. Well, I'm going to define the quantity. Just think of it as a symbol, e to the I theta, to be cosine theta plus I sine theta. If I do this, this is known as Euler's formula. Of course, there's a special case of this that is more typically known as Euler's formula, but this is the thing that gives it to you. But let's just say I'm cheating here, right? I'm going to define e to the I theta to be this symbol. Just think of it as a symbol. Don't think about e as being the exponential function here. This is cosine theta plus I sine theta. If I define this to be this, then this is trivially r times e to the I theta. This is exactly what I'm going to do, but I'm going to not quite do what the textbook does and just cheat by defining this. I'm going to tell you why. Rather than thinking about this as a definition, I'm going to think about this as equality. All right, and I'll give a quick justification for why that is, and then we will proceed from there. Okay, and so that's that. All right, so I will see you all tomorrow at the usual time, the normal time, and hopefully, I won't have to do any of this now. Everything seems fine. Seems like the connection's stable, and seems like everything's set up properly. So hopefully, I won't run into any more issues with that. Yeah, so I will see you all tomorrow. I'll be sending some announcements out a little bit later today.